So hello, welcome back. Happy Thursday. Thank you, global warming, for yet another day in November where I can wear short sleeves to work and be happy with that. See, I'm all for global warming when it's winter in Iowa. Not so much for the other days or the rest of the planet, but let's see. It is Thursday, which means you had nothing due, but you do have something to work on. So your next formative assessment is available inside Icon. It's a story problem that I look forward to discussing next week. Let me know if you have any questions about what I'm looking for. But there's not an obvious correct answer necessarily. So this is meant to transition us from the world of sort of textbook cut and dry into the real world of, well, you could do this or you could do that, and there's reasonable disagreements to be had. Where we are in terms of working through Unit 6, which I think we may finish today, is looking at other types of models for change in which the change is supposed to shut off, and how we can approximate those sorts of truly nonlinear models with linear model versions. So I am on slide 36 of lecture 6 here. That's where this picture came from. Folks with me? Nods or thumbs? Yes, thumbs, nods. You can do both, nod and thumb. Extra credit for nods and thumbs. Thank you. All right, so we talked about thus far two families of models, polynomial models, where we would fit functions of time squared, time to the third power, and that kind of thing, as well as piecewise models or spline models, where we would divide time into sections that correspond to distinct periods given the study design or other factors that would imply a before and after. And what those types of models have in common is that they are still linear models, in that they fit the form of slope times variable plus slope times variable. So even though they're predicting a non-linear effective change, they do so in a linear fashion. So there's terms for that that refer to nonlinear in the variables versus nonlinear in the parameters. The models we've talked about are nonlinear in the variables, meaning that you can add time squared. It's a linear effective time squared, though. So the quadratic slope coefficient enters into the linear model in the regular way. What I want to show you briefly is one example of what would be considered a truly nonlinear model, or nonlinear in the parameters as opposed to the variables. And that's what example 6C is about. But because that requires custom software, I don't know how to do it in 4 different programs, and so I'm doing it in NL mixed as well as a latent basis model, which is another type of estimated nonlinearity. But to illustrate what some of the differences would be, these are data that are related to the data we've been playing with. So we had 6 sessions of practice where the average response time across trials within a session was the outcome. This is breaking down the average response time to each trial within the first occasion. So the black line for what the mean for each trial is in response time in milliseconds is shown right here, and it's a lot messier, as you might expect, given that this is response time data. And I have fit to this 3 different predictions. So the red dotted line is the fit to these means of a quadratic model. So you can see that it has this sort of upside down U shape. And what would a quadratic model predict should happen after trial 30? Where's this trajectory heading? Yeah, back up again, the other side of the U. So from a learning perspective, that doesn't seem like a very reasonable thing. We wouldn't expect people to all of a sudden start getting worse again. We also have a latent 2-piece model that fit with the green line here. So by latent, I mean I estimated where the breakpoint would be as one of the parameters. And it decided that it would fit best at about session 6, or trial 6.5, give or take. And it then fit a linear slope from that point, and then a much shallower linear slope that's actually slightly positive through the rest of these. And so what this green line is trying to approximate is essentially the fit of the blue line. This is the fit of a model that is called an exponential, and more specifically a negative exponential because it's slowing down. So the blue line does a much better job of capturing the idea that at some point people are going to hit asymptotic performance, meaning like the best they would ever do, even if you let them practice forever and ever. So what makes the exponential model different is that one of its parameters is an asymptote for ultimate differences in level. And we would have a fixed asymptote that characterizes the ending point on average, as well as potentially a random asymptote that captures individual differences in where people end up. So here is one way that we can set up a negative exponential model. There are alternative parameterizations, but the one that I'm using has 3 different parameters, which I'll demonstrate here. So one of those parameters is an asymptote. And in this context, we're talking about a lower asymptote because response time is going to keep improving up to some point where you just can't get any faster. This is as fast as you can do this task. And these 3 lines differ in their asymptotes. So the person in the red here would have a best eventual response time of 1.8 seconds. The person in the green gets all the way down to 1.5, and the blue person gets down to 1.2. So these functions differ only in their asymptote for where they end up. The other parameter that captures the total amount of change is shown in the bottom left picture here. And here, these 3 lines differ only in their amounts. So the amount you can think of as the total distance from the starting point to the asymptote. Consequently, another way that people parameterize these models is to replace amount with intercept. So these 3 lines differ in where they start, and consequently, they must differ in the total amount of improvement that it takes to get down to this common asymptote. So it's one or the other. And you can take asymptote plus amount and get back to intercept as the initial predicted starting point for these functions. Both of these enter into the model linearly. The nonlinear parameter is a rate. And so this corresponds directly to what people talk about more colloquially as a rate of learning. So how fast can you get better at this task? And these 3 functions have the same asymptote for where they're going to end up. They have the same total amount of change, which translates into the same intercept starting point, but they differ in how fast they get down to the asymptote. So the blue person hits it the fastest, followed by green, and then the red person is the slowest, and they're not quite at asymptote by session 6, but if we watch this curve keep going, they would eventually end up where blue and green are. So this is the parameter that makes this tricky to estimate, this idea of a rate. But in terms of describing individual differences in learning, the amount of learning that's happened and the rate at which it occurred are things that people tend to care about. Also, asymptotic performance at the end of training is one way to try to make people equal with respect to the effects of practice. Like, let them practice as much as they need to until they can't improve anymore, and then that final value is an indication of their optimal performance at that moment in time. Okay, how are we doing so far with pictures? Okay, so these are the 3 parameters in this model. The name of the exponential model, positive or negative, describes which way the trajectory is accelerating. So if it's accelerating, like going crazy, that's a positive exponential function. That would be something like bacteria growth on a sponge, like increases exponentially. COVID rates at the beginning of the pandemic increasing exponentially, fortunately not so much anymore. So a trajectory that is slowing down, that's decelerating, we would call a negative trajectory. So going up and slowing down, or going down and slowing down, those would both be negative functions from the perspective of this model. So the amount reflects the total distance from the asymptote back up to time 0, and it's multiplied by e to the rate times time. So this is the nonlinear part of the model. And because of this nonlinear part, we can't estimate this in standard multi-level modeling software. We have to find something to where we can control the model and estimate it how we want to. In SAS, I use NL-mixed for this. I am quite certain there are comparable routines in the other packages, I just haven't learned them yet. So this is what the model looks like. Level 1 looks a bit different than usual. because of this e to the beta 2 times time. So this version of the model, beta 0 is not the intercept. It's an asymptote. So what is the eventual best level of performance they get to is beta 0. And then the rest of the model gets us back up to where we started. So beta 0 then, with an I, is a placeholder for how each person would get their own asymptote, and that could have a fixed part at a minimum, which would be the mean for the sample, plus the individual deviation given by a random effect. So this is individual differences in level of performance, like we're used to thinking about, but it's optimal level. Beta 1 is the amount of change, and that can have a fixed part and a random part. So people can differ in the total amount of improvement that they exhibit relative to where they start to where they end up, the asymptote. And then the rate parameter can have a fixed part and a random part. And the random rate in particular, I have never been able to estimate in real data. That's the one that's tricky. Random effects inside the exponent here. That's the part that takes a lot more data, and it's very tricky with the examples that I've captured. So this is the type of model that I would recommend if you have enough data and you, how do I say this? You're willing to go to the extra trouble to fit the nonlinear function. But if it's something to where this is going to cause problems, then I want to show you a shortcut instead that I discovered after I wrote my book and which is going into the second edition. So one of the catches with estimation here is in switching to a user-defined type of estimator like NL mixed, we have to switch to maximum likelihood. So that's not great for small samples. NL mixed also doesn't have built-in things for degrees of freedom, and most of the analogous nonlinear solving parsers and estimators would not either. So I want to not spend class time on going through the NL mixed code because I recognize that most of you are not SAS users. So I was going to make a video about example 6C and post that separately for you to watch. Here is how to cheat your way into something that looks like an exponential model, but is still estimable in standard multi-level or growth modeling software. So if we want to do something that's faster and easier and in which RUML estimation is possible, the easiest way to trick your model into looking like an asymptote is to log transform your time predictor. So these pictures show on the bottom, the x-axis is natural log transformed time. So if time starts at occasion 1, 2, 3, 4, then the log of occasion 1 would be 0. So 0 is the start of the x-axis in these pictures. The black line shows what would be predicted by a linear effect of log time. So there is a linear relationship between the outcome and log transform time that's positive in the bottom left picture, it's negative in the bottom right. If we take log time as a predictor and we square it, then we can enter a quadratic effect of log time that bends this line a little bit. So a positive quadratic would bend it up, a negative quadratic would bend it down, and vice versa for the negative thing. But when we back transform time into the original variable, that's what's shown here in the top two pictures. In particular, look at the blue line. Doesn't that look an awful lot like an asymptote? It looks a lot like an exponential function. It's not a true exponential function, but it's pretty good approximation. So a quadratic and linear slopes for log time is a way to use a polynomial model to get something that looks closer to an exponential prediction. But it's still a linear model, which means it's easier to estimate. So the top left picture then is a positive slope of log time linearly, and then paired with either a positive quadratic slope or a negative quadratic slope. And then the top right picture is a negative slope linearly of log time paired with either a positive quadratic or a negative quadratic. All right, so that was the one that I wanted to test out and walk you through the model comparisons that will be involved in evaluating that. All right, any questions so far? You want to see it? Why not, right? So this is example 6D, using the same data. These models are not in my textbook, so this is bonus material relative to what that offers. It is going in the revision, though. In terms of the data prep, the only new piece is creating a logged version of time. So this is not a link function. This is a data transformation. And I know that sounds crazy coming out of my mouth, but sometimes data transformations make sense. In this case, I'm not transforming time to make it more normal or more regular or reduce skewness or any of the things that you would normally transform data for. I am doing it so that I can approximate an exponential curve using a linear model. In SAS, the function that makes a natural log transform is LOG. This will differ across packages. For instance, in Excel, if you type LOG, that's log base 10, whereas LN is natural log in Excel. In Stata, it is lowercase log for log time. And in R, let's see what it was. Anybody know? Lowercase log. Okay, so they're all relatively consistent within that, but just if you're using some other package, make sure to look that up. We don't use log base 10 for anything really in statistics. It's all natural log. And keep in mind that you can only take the log of values that are above 0. So you may have to move time over if it started at 0. Just add 1 to it and then take the log. But in this case, session 1 becomes log time equal to 0. The other piece of this is that I'm adding the dummy codes because I'm eventually going to want to test absolute fit. And so that's the way that I will plug the holes that the fixed trajectory leaves in the model for the means, and we can test whether this model is sufficient. So any questions on making variables and such? In Stata, I had to make a squared version of log time because it wouldn't let me make the squared version as a random effect in the model syntax. It kept yelling at me, and I was like, all right, fine, I'll just square it myself.
Lisa,
Problem solved.
Yeah. So the reason why we're taking the log is to have that upper asymptote, like the ceiling effect. Because if we're talking about learning, for instance, you don't want to continue learning, forever. You reach like a point. But what I'm curious about is, does that change the interpretation at all of the, defining the relationship of time?
Yes. Yes, it does. So to answer that question, let me show you the code that I use to generate predicted outcomes at each occasion. So for instance, these values right here, this is what the log of time is at each subsequent occasion. So you have to think about this as a 1 unit change in time is not per session anymore. It's in whatever log metric we're talking about.
So you have to basically inverse link it, for lack of a better word, back to, you'd have to exponentiate it to get back to the original metric. Oh, okay, that makes more sense.
Yep, e to the log time gets you time back. So that's where these pictures in slide 41, that's how I made them. The x-axis on the bottom is is log transform time, and then I exponentiate the predictions from log transform time as the predictor into this picture where original time is on the x-axis instead. So what a 1 unit change means differs because you're in a different metric. And it's a little bit harder to think about a unit of log time. As you can see, it's uneven, but that's exactly the point. We are creating a function that slows down the further into time you go, because that's what we want to happen. Okay, does that answer your question?
Yes, and just kind of furthers my whole belief. Everything is just on a log scale. I just feel like
Logs are useful.
they are.
I can't say that I understand them as well as many of you probably do, but I have seen them come in handy in a lot of places. So if nothing else, log is a button on your calculator or a function in a program. But it's a transformation that takes large numbers and condenses them, and it takes very small numbers between 0 and 1 and spreads them out on the negative side. So that's my layperson's definition of what a log does. So the only switch to the models then is what I'm putting in the parenthesis in level 1. I'm putting in log time. And generally speaking, when I put in predictors in these sorts of equations, I also show the centering constant. So like I would have session minus 1 as a predictor variable, or time if I've defined it that way in the writing. And so this doesn't need a centering constant because the log of occasion 1 is 0. So we're starting with just a fixed linear effect of log time and only a random intercept in these models. So the code looks very similar to what we've seen up to this point. I put in log time as a predictor, as a fixed effect only to start with. And we're going to compute effect size via pseudo R-square. I'm asking for predicted outcomes at each occasion so that I can make a plot and see how well I'm doing. Also storing the results of these models in preparation for a likelihood ratio test. And here's the Elmer code, again back to Elmer because we don't have anything in the R matrix besides a diagonal residual variance. And here's what we get. So our V matrix here is constant variance, constant covariance, otherwise known as what? Vocabulary exercise? Compound symmetry. And is that a coincidence or consequence of my model here? Yeah, the answer is always consequence when I say that question, by the way. I'm just trying to be clever. But yeah, it's a consequence because this model has only a random intercept in it and only a residual. So that is a parallel growth curve kind of structure where we have constant variance and covariance. And the predicted correlation over time, if we translate this covariance into a correlation, is also constant, 0.86. So this has a special name. 0.86 is telling me about what? Starts with an I.
Is that ICC?
Yes, it is. And in this class, ICC stands for what? Intraclass correlation, yeah. Not item characteristic curve. That's in an hour and a half, give or take. So 0.86 is how correlated the occasions are from the same person after we control for a linear effect of log time. So I would call this a conditional interclass correlation because it's after predictors to some extent. So there's a lot of constancy implied by this model in how people perform on this task. Survey says, does log time help our model as a fixed effect? Yep. And do I have to do a likelihood ratio test or any of that? Or can I just stare at this p-value? Just stare at it? Sound like a plan? Could I have done a likelihood ratio test? Let me phrase it that way. Using REML, which is what I'm using. No, I could not. Yeah, so in REML, we do not use likelihood ratio tests for models that differ in fixed effects, only for models that differ on their variance side. So when adding random effects, when adding structures to the R matrix or anything like that, that's a likelihood ratio test. Fixed effects, we can just stare at the p-value. Because the null hypothesis of 0 for a slope is a reasonable thing. So minus 156 is the rate of change per unit log time. And then someone's going to be like, what the hell is a unit log time? And I would say, good question. Please see figure 1 for a picture. So the yellow line is the prediction from log time. And damn, doesn't that look pretty? These are real data too. This isn't even like, me like stacking the deck. This is real data. So these are the predicted outcomes at each occasion as created from estimate statements, LINCOM statements, or contest 1D. There's other functions you can use to do the same thing, but this will help us to judge how well our fixed effect trajectory captures these saturated means. In terms of effect size, let me get to the model here. I've got two different kinds of variability in my model. Which one of those should have been reduced by adding in a fixed effective log time? Level 1, because log time is a time varying predictor. So relative to what the model was without it, then this is what it became. I did a pseudo R-square against the empty model, which is not in this handout, but it was shown in example 6A for the same data. And it looks like we have accounted for 24% of the variability at level 1. So of all of the variability that was within persons, 24% of that, give or take, is because of constant differences over time that people share. And should we make it random? Why not? That seems like a reasonable thing that people would differ in their change over time. Yes, sir?
Can you go back to that pseudo R-square? Because that almost 24%, it belongs to the 17% of variance within units, because we saw that the ICC is 85%, right?
Well, this was the conditional ICC, but yeah, I think the one from the empty model was around the same. I think it
Okay.
was like 0.84 or something.
Okay.
So yes, of the percent that was within persons, we got 24% of that
Oh,
percent.
okay.
Yep. And I would phrase it that way because it's important to be specific when you're trying to explain multiple piles of variance at the same time. Yep. Okay, other questions before we look at the next one? Zoomers, you with me okay? Thumbs, excellent, thank you.
I wanted to ask, so are we basically using a GLM to model the effective time? Would that be considered GLM, or is it just transforming the data?
Transforming the data.
Okay,
Because, so by GLM, do you mean generalized linear model?
yes.
Okay, so generalized linear models are, what they do is they transform the predicted outcome via a link function.
Oh, and we're not doing that.
We're not doing that. We're not touching
Okay.
response time. And we're also not, and those models don't transform the response time outcome either. They transform the conditional mean to be predicted. And so this is just, I'm just transforming the predictor to make the shape that I want. That's
Yeah.
all.
That makes sense.
Yep. So it's a easier way to approximate an exponential function. That's what I'm doing here. Okay. Now what I'm doing here is adding a random slope. So this is allowing then individual differences in change over time, following that same sort of exponential-ish kind of function. So log time then goes into my random line here. Log time goes into Stata code right there, and log time goes right here in Elmer as well. So now, how many ways do people differ from each other according to this model? 2. So another way of saying that is, what's my dimension of the G matrix? 2 by 2. People differ from each other in intercepts from where they start, and they differ from each other in their subsequent linear rate of log time change. So it's still a linear model technically, it's just that it's a linear slope for the log transform time variable as a predictor. So the V matrix has a pattern to it that is no longer compound symmetry. This type of model predicts variance that changes quadratically over time, so variance in a U-type shape where there's some minimum. Likewise, correlations that are predicted to change over time in a time-dependent pattern. We have 2 new parameters added, the covariance between the intercept and the slope, as well as the random slope variance. Those 2 new parameters, if we do our likelihood ratio test, survey says, yep, definitely helps. Here are some confidence intervals to try to describe the size of the variation. So intercept confidence interval, linear slope confidence interval. And once again, it's overlapping 0, meaning that some people are actually predicted to get worse, not better. So this looks pretty good to me. Let's see if it's good enough. So I'm using the same new trick of saturating the means to decide if the trajectory that's being created is sufficient to recapture all 6 means. So do you want to walk through the logic of this again? We did this on Tuesday, maybe good. So if I have 6 occasions, then how many fixed effects does it take to fully predict those 6 occasions? The total of 6, though. Total of 6. Now, what do I have in my model? How many fixed effects did I have before? 2. Log time is one of them. What's the other? The intercept. Yes. So given that I could spend up to 6, and I've only spent 2, that's how I know that I need 4 more. So these are dummy codes that indicate which session it is. So it's 1 if it's session 1 for S1 and 0 otherwise. In this case, I could pick any 4 because this is a continuous function that won't be perfect at any point. Previously with the piecewise model, I had to stay away from 1 and 2 because that part was saturated already. And to lump these 4 dummy code slopes together, that's an extra line of code that I need to do. So this is contrast to do so in SAS. So the commas separate numeric degrees of freedom, numerator degrees of freedom rather. And in Stata, that's the test command to do the same thing, where numerator degrees of freedom are separated by the parentheses, and the equals 0 is there to make it explicit what I'm testing. And in R, the same thing with more typing, is lumping together 4 in this case, different slopes, one at a time, in terms of its relative position. So again, relative to the order in which it is returned by the fixed effects in R. It matches, in this case, what I wrote. So this idea of lumping slopes together is much more general than this. You can do this anytime you have a hypothesis that involves multiple slopes for one concept. Okay, questions on that? Survey says, yeah, go ahead.
Yeah, in R, the order of your fixed effects is the same in the R bin option, because there I can see, for example, you have 0, 0, 1. I'm assuming that the first set is for the intercept, the second should be session 1, but there you have the 1.
So the first 2, its intercept is the 1, the slope of log time.
Okay.
So that's why these are zeroed out in every place, because I'm not interested in those.
Okay.
I'm interested in the ones past it. In general, every time that I realized that R rearranged the order in which I wrote these, I've gone back into the code and made it consistent. When it does it is when you incorporate interaction terms, because it insists on having all the main effects first. I'm sure there's others, but that's the time that I've seen it happen that's relevant in terms of this type of material. So yes, the reason that it's zeroed out in every spot of these is because we're not interested in testing 1 plus log time. We're interested in the joint contribution of those 4. So we have their individual contributions here looking non-significant. That's off to a good start. And then the joint hypothesis test. So this is either going to be rendered as a chi-square or an F, depending on whether or not you're using denominator degrees of freedom. If you are, then F is per slope. So F times numerator degrees of freedom is your chi-square. So you can get from one test statistic to the other quite readily. And each of them then has their own reference distribution for what F would be and what chi-square would be. And as you can see, they pretty much agree. So survey says non-significant. Yay or boo? We got 1 vote for yay. Another head nod for yay. 2 head nods. Zoomers, what do you think? Yay? Oh, we got the happy. Yeah, that's a good one. They have the confetti icons. That does mean yay. That is correct. Yeah. So yay, and also as written right above it, the idea is that if our model did a good enough job recreating the 6 means, then these extra 4 dummy codes shouldn't have anything to do. And they don't. That means it's good enough. So we're halfway there. Our linear slope for log time appears to be sufficient to describe the pattern of mean change, ... What else do I need to worry about? Besides the pattern of mean change, let me say that with more emphasis. What's next? Variance. Yeah, more specifically, what kind of variance? I'm watching the chat window or I'm listening. What about variance? Variance model? What's in my variance model at this point?
Just the random intercept and random slope for log time.
Yeah, this model, if I go back to the equation, I have an intercept and its variance, random slope variance, their covariance between the two, and then E has constant variance across occasions with no covariance in the R matrix. So that's actually just 4 parameters. And I'm asking those 4 parameters to do the work of 6 different variances and what, 15 covariances? Does that sound right for 6 occasions? 6 times 7 is 42 divided by 2.
21.
Yeah, 21. So yep, that sounds right. 6 variances and 15 covariances. So these 4 parameters are supposed to do the work of 21 parameters. That's the other part that I got to worry about. So then to answer that question, I am estimating a comparison model that keeps my linear slope for log time in the model for the means, but switches it out for an unstructured R matrix. So this is the best possible model for the variance that I can have, keeping the fixed effects constant. And I want to do a likelihood ratio test to see if my model, which has random effects in it, does as good a job as the perfect model. So we're going for not worse, not significantly worse. And to do that in proc mixed requires just taking out the random line and switching R to unstructured. Likewise, in Stata, I take out the no constant, so that shuts off the random intercept, and I take out the slope, and then I switch the residuals to unstructured, and in R requires moving to a different package. So I have to switch back to GLS, which is in the NLME package, because Elmer does not have an R matrix that I can mess with. So then I've added these 2 pieces to the model, where the first part gives me the unstructured correlations, the second part gives me heterogeneous variances. Then to make the comparison, I re-estimated my, oops, shouldn't be random quadratic, this should be random linear log time model. So I just changed the comment right here, my bad, to using LME so that I can have the random intercept and slope as my point of comparison. Survey says, deviance difference, -2 log likelihood difference of 58 on 17 degrees of freedom. Wah, wah. So what this is telling me is that my model is significantly worse than perfect. So my 4 parameters are not yet doing a good enough job capturing the pattern of variance and covariance over time. And here's a picture that shows the predicted variance from the random linear log time model versus unstructured, and you can see that it's off a little bit. So what if we throw quadratic log time in there? Could we do that? I just did. So log time squared. So this is still technically a linear model because it's linear in the parameters. It's slope times variable plus slope times variable. But it's creating this complex nonlinear function by making a quadratic slope for log time. No worries, How we find the predicted outcome at any occasion is still the same way. Whatever the fixed intercept is, plus the fixed slope for linear log time, fixed slope times log time, plus the quadratic slope multiplied by log time squared, or how we would get the predicted instantaneous linear slope at any occasion starts off with what it is when log time is 0, and then twice the value of time that you want the linear slope for multiplied by the quadratic coefficient. So multiplying the quadratic by 2 is how we get to the rate of acceleration or deceleration. On its own, it provides half of that. So then the predicted outcomes here, here's what log time squared becomes. So an even stranger metric. And here is log time times 2. That's what these numbers are here for. Log time by log time is my new fixed slope in SAS. Log time by log time with a hashtag or a # is in Stata. And in R, it's the I and then log time caret 2 in parentheses is one way that I found to do this. And so then I have the predicted intercepts and slopes at each occasion for all of the possible occasions. So I'm adding in, let me back up here for a second. I am adding to the fixed effects part of the model, even though my linear slope for log time was enough. The reason for that is because I'm eventually working my way up to random quadratic. And in order to have a random quadratic effect of log time, I have to have the fixed effect too. So it doesn't make sense per se to look at this model as an improvement in the fixed effects, although you'll see what happens. But it does make sense as a building block to get to a better model for the variance. So here's what happens. We still have our 2 by 2 G matrix because we haven't changed the variance side of the model yet. And lo and behold, it actually did help a little bit. So even though our previous test told us that our model was sufficient with a contrast of 4 degrees of freedom, adding one of them back nevertheless improved the model. So it looks like there is a little bit of deceleration of the effect of log time. And if you're like, what do I do with these numbers? I would say, see figure 2. Because at this point, trying to explain what a quadratic effect of log transform time means is, your readers are not going to stay with you. But they'll follow the picture. So the difference then is the yellow line versus the green line. And the green line does indeed look like it fits a little bit better. So either one of these looks like it would be enough, but the green one gets the nod. So that is making the yellow line slow down a little bit. So whenever the signs of a quadratic and linear are an opposite, that's a slowing down of the function. They're working against each other. So the negative slope is being slowed down by twice the quadratic per unit time. And so then I have where these numbers came from in terms of the model out here as a reminder. In terms of pseudo R squared, the new effect of quadratic log time captured another 1% of the variance that remained, so a small effect size, but still significant. And then last but not least, random quadratic log time. So we add U2 here to see if there's individual differences in deceleration. And this is the point, Stata users, where I had to use log time squared as a variable. It wouldn't let me do log time times log time in the random part of the model. I don't know why. In R, it was fine with that. So I have this I log time squared thing and the random function, as well as a fixed effect over here. And I have a note that this model reported a convergence problem in R, although it was fine in the other pieces of software. So something with Elmer does not like quadratic slopes, it seems. So now our model says that people differ from each other in how many ways? Our people differ from each other in how many ways according to this new model? 3. And how do you know that? Because I've highlighted the 3 by 3G matrix. Yeah. So the U's, how many U's are there? Yeah, 3. So people differ from each other in 3 different ways according to this model. Another way to say it is that there are 3 distinct sources of person dependency that are contributing to the correlation of occasions from the same person. So we have a new pattern of heterogeneity of V that has a quartically changing pattern of variance as a function of time to the 4th. We have a likelihood ratio test that's going to tell us whether or not this helps. It looks like it definitely does. But I also want to point out a switch in our conclusion with respect to the fixed effects. Look at our new, formerly new effect of quadratic log time. It was significant when it was only a fixed effect, and now it's not. So this will happen to you because anytime that you add a random part to a fixed part, the standard error is going to increase. The standard error for a fixed slope has the random slope variance in it in the numerator in addition to the residual, whereas it's only residual otherwise. So it looks like on average, according to this model, now there's not evidence of acceleration or deceleration on average across people, but there is evidence of individual differences in that given the likelihood ratio test against the comparison. So in addition to testing hypotheses about individual differences, for proper inference about the fixed effects, you need the random effect with it if it needs one in the model. Question, does the increase in SE mean we need more power when adding random effects? That would be one way to interpret it. I think the way that I think about it is that the previous model had a false sense of security in how precisely estimated this effect was. It didn't take into account that people needed their own version. And so after we introduced that source of variability that was lurking in the data but not operationalized as such, then the standard error is bigger because it really is less precise. Because if this effect differs across people, then what you get on average is going to fluctuate more across samples. So then, should we take this out since it's not significant or leave it in? We keep it, right? Why do we keep it?
Because we don't have random without fixed.
Yeah, because we have the random over it. So we keep it in even though it's not statistically significant, because otherwise the random effects would have to deviate from exactly 0 rather than deviating from this coefficient of 47 that is optimal. So we keep it in. And here's some confidence intervals for effect sizes. And for the last time, is it okay that these confidence intervals overlap 0? Yeah, that just means that some people go up and some people go down. It doesn't mean the fixed effect is not significant. So then if we go through the same process of testing absolute fit, I would expect that on the mean side, our 3 remaining dummy codes don't have anything to add because the 4 didn't before. So we lump those 3 together. Survey says, indeed they don't. So even more non-significant result than the last time. Now the variance side. So I'm re-estimating the model with a different variance structure, unstructured R matrix, to serve as a comparison to see if the 3 random effect model plus residual is enough. Had to switch to GLS and LME to do that in R, of course. Survey says, non-significant. We win. So yeah, this one looks like it does as good a job recreating the 21 variances and covariances using 3 sets of random effects, their covariances, and a constant residual variance at level 1. Okay, how are we doing? Good. So then the grand finale. I fit a whole lot of different models to these data, so I wanted to do a little bit of comparison across families. So I have the winner out of each combination here, and the original Excel tables that I made these out of are in your download folder. So I have random quadratic time as our best fitting polynomial model, but relative to the right answer for saturated means and relative to the right answer for unstructured variances, it wasn't good enough. Then we tried piecewise models. So a piecewise model with both slopes being random was not worse than saturated means and not worse than unstructured variance, but it was theoretically dissatisfying. The one that you haven't seen yet, but just to let you know what happened, the negative exponential, so the truly nonlinear model, had a random asymptote, so people differed in where they ended up. They had a random amount, so people differed in how much they had to change to get to their asymptote. But the model with the random rate blew up and I couldn't keep it. So I kept it fixed, and this negative exponential model did a good enough job on the mean side, but not a good enough job on the variance side. The random linear log time model that we looked at in this example, also good enough on the means, not good enough on the variances, whereas the random quadratic version of log time that we just finished with, good enough on both sides. So to me, it looks like the common denominator of what works and what doesn't with respect to the variance side is that the models that say that people differ from each other in 3 ways are all okay, except for the first one here. So this one and this one. The models that say people differ from each other in only 2 ways are not okay. So which one you would go forth with depends not only on which one fits best, but also which one matches what you want to say or ask about your data. Random quadratic time is really the only one that you could not make an argument for. The negative exponential, I would say, probably shouldn't make an argument for. So piecewise or random quadratic log time would be what I would go with. Piecewise will be easier to explain to people, but perhaps harder to defend the fact that you have this not point for no reason after session 2. There's one more that I wanted to let you know exists in the world, which is a latent basis model. I have slides on that. I'm almost positive I do. So to find it, skip the words. Yeah, okay, let me show you some pictures, okay? So for those of you who haven't had SEM yet, no worries, you're not going to be responsible for this, but for those of you who are learning those models, I wanted to provide this as a tie-in to the other class. So this is what a quadratic model would look like if we estimated it as a single level structural equation model. In the advanced longitudinal class that I'm doing at this same time next semester, we will get to know longitudinal models using both single-level structural equation modeling as well as multi-level structural equation modeling, because those are what we need to model time-varying predictors appropriately if they themselves have individual differences in intercept and change. But this one is mapping on all of our multi-level parameters onto the picture here. So each circle is a random effect, is a latent variable. Random effects and latent variables are the same. The means of the latent variables are the fixed effects. They are the gammas. The variances of the latent variables are the variances of the u's. And so this part of the model up here with the random circles is essentially the G matrix. The bottom part here, the occasion-specific residuals, which I've used one common circle-looking thing to convey the fact that we're holding all of their variances equal to each other. And the loading pattern, so these numbers right here, these are fixed. So these are used to define what the circles are supposed to mean. So any random effect / latent variable that has equal loadings like this, you can think of as a random intercept. So this is essentially like a Roche model kind of idea in terms of measurement. A Roche model, in that case, theta is a random intercept. And you can estimate Roche models using multi-level modeling software for that reason. This circle I know is the linear effective time because of the loadings and how I've defined them. And further, I know that my intercept has now become conditional on the first occasion because that's when my loading is fixed to 0. And these numbers over here on the right are squared time. That means I know that this is a quadratic model. So how would I have to fix this to turn it into quadratic log time, do you think? Because I can do it. It takes one set of swaps, as you were.
You have to change the loadings on the L2 circle.
Yep, both of them. So I would change, I would change these values to whatever log time is at that occasion, and I would change these values to whatever log time squared is at that occasion, and then I'm right back to the best fitting model that we left off with. Now, why would you do it this way? If you have enough people, and maximum likelihood estimation is going to give you the same answers as residual maximum likelihood, that's one concern. If each of these boxes was actually itself a latent factor, so you wanted to have items indicating a latent variable at each occasion, and then you wanted to see how those latent variables grew, that's why I would do it this way. If people need their own version of time, so if there's unbalanced time, not everybody's on the same schedule, you would need software that allows that, such as T-scores and M+, and I have yet to find a comparable version in Lavaan. But here's another option within this framework that you can also use. This is what's called a latent basis model. And you have a reading on your reading list for this class. It's McNeish 2020-ish, where he has a good treatment of this as well as an extension. But here, the difference is that rather than defining the factor loadings to represent some kind of specific pattern of change, linear or quadratic or log time or whatnot, I'm letting the data figure it out. So the basis of change is being estimated. So the rules are you fix 2 of the loadings to known values, and you let the data decide what the rest should be. So the most common parameterization of this is 0 for one of them and 1 for the other. And if you do it that way, then you can think of these loading values as indicating the proportion of change that had happened by each occasion. You can also scale it to reflect not just a 1 on the end here, but how much time has passed. So like if I made this a 5 instead, then these numbers are going to be in the scale of time itself. Same thing if I did 0 and then I did -5 over here. So that's one way that you can make the coefficients on the same scale as other models. For these data, here's what the code would look like. This is M+. So this is a random quadratic model on the left-hand side, and this is Lavaan code on the right-hand side. Or nope, sorry. This is the quadratic model on the left-hand side. This is the latent basis model on the right-hand side. This is all M+ code. And the basis estimated loadings were 0.57, 76, 90, and 98. So based on that, it looks like if the first occasion is 0, the second occasion is 0.57, that means that like 57% of the change has happened by the second occasion. And then 76% of the change had happened by the third occasion. And that matches reasonably well to the picture, if I can find my picture again. There it is. So half the change basically had happened by session 2, then it keeps going. And so like by the time you get from 5 to 6, there's not much more there. And that's reflected by an estimated coefficient of 0.98. So why one would do it this way, here's the Lavaan code, by the way. I knew I had it in here somewhere. Why someone would do this is if you're interested in having only one latent factor to talk about change with. That would be the motivation for wanting to try this, because then the model simplifies if this latent variable is meant to be a predictor of other things. Because otherwise, let's say that I wanted to test how change over time related to eventual health or something like that. So So if I had some box over here that these circles were supposed to predict, then having linear time and quadratic time both predict something else, do you think they're going to have some collinearity there probably? Like time and time squared going to have something in common, and they'll fight against each other? So that's less convenient than trying to use one latent variable to capture nonlinearity. So I fit this model to our data. I knew that was close to the end. And the fit of that model, unfortunately, here we go. Here it is. So the latent basis model I threw in here as 8. It has the same number of parameters as the other models that have 3 sets of individual differences because it spent those parameters on loadings instead of additional random effects. So it's a non-nested model. So this is an instance in which if I wanted to talk about relative comparisons of these models that each have 10 parameters, I couldn't do it with a likelihood ratio test because I have no degrees of freedom. I have to do AIC and BIC. So AIC and BIC is relatively happiest with random quadratic log time. Latent basis is decidedly worse than those two. And again, I think the reason is that latent basis is reducing random slopes into one kind, whereas all the other models that fit adequately have 2 kinds. So there's 2 different ways that people are changing is sort of the common denominator of what seems to fit across these models. But these are all re-estimated using maximum likelihood so that they're all comparable across either means, variances, or both. So I do have at least one paper using latent basis if anyone is interested. And then, yeah, here's the article that I was referencing. Because in addition to having these loadings be estimated, you can have them be random. So you can have each person have their own data estimated trajectory. And you can do that in M+. All right, there. I think we made it through like everything almost. And I will, in example C, this is example C here, I'm going to make a video about this and post it separately. But just to give you a flavor of what this looks like, NLMix code looks similar to what you've probably seen in like Stan or JAGS or any of those other Bayesian programs where you have to write everything out. In NLMix, you have to write out all the parameters that you want to estimate and give them start values. You have to set up your level 1 and level 2 equations. You then have to define the conditional mean and variance for your outcome, define any random effects, and everything else. So NLMix in SAS is one way that you can estimate anything, basically. It's set up for 2-level models that can be generalized or multi-level as needed. And so I have examples then using this code to do empty models and random quadratic models, since we know how to do those, and then going into the family of negative exponentials. And at the end of the handout, I believe I put in latent basis as well. Let me see if that's true or if I'm just making stuff up. Oh, I tried to do it in NLMixed, but it didn't like it very much. So then I did it in the other software packages. So in the download folder for this unit, in R and M+, there are latent basis inputs and outputs so that you can practice with those if you'd like. But you can also do, again, this is a latent basis structural equation model using NLMixed as well. All right. So I think I've hit everything that I pretty much wanted to say, which is a miracle. Questions? Zoomers, questions. Roomers, questions. So where we're headed next then, ... What's your question first?
Yeah, it is a small question because at the end of the comparison table, we can see that between families of models, the difference in terms of the AC and BC, for example, between random quadratic log time and latent basis, the difference is almost marginal. What happens if I want to work with the latent basis model because it's easier to understand or maybe to work with, but I see that the AC and BC support the other model? can I justify my decision to work with any model based on theoretical things or practical things, or do I have to respect these numbers, although they are almost marginal?
Respect the numbers. I like that. So let me translate the question in case the Zoomers didn't hear you. I think it was, do I have to obey these results, or can I bring theory and design into my choice of model?
Yeah, exactly.
And the answer is yes. You have to obey the results to an extent, I think. So in this case, like, based on what fits and what doesn't fit, so this bottom comparison right here, because I'm in maximum likelihood at this point so that I can compare all the different models, because latent basis and negative exponential are only available via maximum likelihood, I had to re-estimate all the others in ML to make it comparable. This chi-square and p-value right here, this would be the SEM test of absolute fit relative to the H1 model. That's what this would mean, because it's testing both sides at the same time. And based on this, piecewise or random quadratic log time both look like they fit okay. Latent basis does not, and the others do not. So I would say that if it comes to picking piecewise or random quadratic log time, you've obeyed the data to that extent, but then which of those you prefer can and should be informed by theory, questions, design, and all the other stuff. I don't think that you can make a theoretical argument to use a model that has been shown not to fit. Like, that is a reach to me. I have seen people say, well, the likelihood ratio test was significant, but the BIC liked it better, and I'm going to listen to the BIC. Yeah. Like, that's a little bit squishy to me as well. But there will be cases in which the BIC doesn't like a more complicated model because of the parsimony correction, but the likelihood ratio test says you should keep it. Nah. So I think that, which family of models that you would choose for a given project should be informed by both what do the data look like? Like, if you make a plot, does it look bendy? Does it look discontinuous, or does it look continuous? But it also has to be informed by the context. Like, if this is a learning study, I'm not going to be inclined to agree with the polynomial models because they say that people, like, unlearn at some point, and that's just, like, that's not what should happen. So I think there's room to make arguments, but I do think that your argument should be informed by the data and what you found with the comparisons, with all the usual caveats about power and whatnot too. If you only have 10 people, all of your models are going to fit because you have no power to detect misfit. All right, other questions? So then where we get to head next week, it looks like, I will post a video about example 6C, and I will put up new stuff because now we get to transition into the idea of using predictors, time invariant predictors of individual differences in change. So I have a review lecture, and then I have another lecture about that in examples, and then we'll be done with the semester, if you can believe it. We're in the home stretch, folks. We really are. So what you have to work on for right now is your next formative assessment. There's another formative assessment due after that, and then you'll have another homework, and I'll let you know as soon as those next things are available. But for right now, you just have to do the story problem. Sound good? All right. Anything else before we call it a week? All right, then I will take that as a no. Thanks for being here. Good to see everybody. See you next week. Bye, Zoomers.